Okay, we have a couple minutes. See, in the past, did anybody answer questions, but I didn't actually give you anything? Has anybody answered questions in class, but didn't get a little souvenir that would like a souvenir? No? Oh, Louis, are you sure? Do you want a wafer? Yeah, why not? Okay. Can you pass that back? Yeah, I didn't bring enough in the past. Oh, okay, that's a good question. How much, so typically in a modern semiconductor fab, the state-of-the-art fabs use 12-inch diameter wafers, and the cost of a fully CMOS processed wafer is a few $1,000s. I mean, that's the value, and then you would dice it up into chips and package it and sell it, I don't know, for $1 or so, I mean, depending on the chip. So basically, the value of a wafer is thousands of dollars, if you know what to do with it. But probably for you, it's probably like a Christmas ornament or something. But it's sharp, so be careful not to break it. Yeah. Is there anybody else that I sort of, okay, who has answered? Can you pass that back? All right. Were there any questions left over from last time that I didn't have a chance to address? Huh? Did you get a wafer already? Okay, fine. All right, so I have all these wafers because I took a couple of years off from teaching to work in the industry for a couple of years, and we worked with a foundry to make some memory chips, and that's why I have a whole bunch from experiments we ran. So they're not any good to me anymore, but I figured they're nice souvenirs for you. Okay, so why don't we get started with lecture 7. So today we're going to cover the very first simple example of a semiconductor device. Well, I forgot, there was one more basic material property that we should review, and that's the work function. All right, so a metal semiconductor contact might sound really boring to you, but actually it's quite useful, and it is important to understand how a metal semiconductor contact should be designed to perform the function that you want it to. So in a semiconductor integrated circuit, we have metal semiconductor contacts pretty much wherever we want to conduct current into and out of a semiconductor device. Okay, so if we look at let's say, schematic cross-section of a MOS transistor, so the gate controlling current flowing between the source and drain regions, current flows into and out of the transistor through metal wires that physically touch the semiconductor to allow the current to flow in and out. So for this particular application, you would like to have current flow into and out of the semiconductor easily. For other applications, you would like to actually have it flow in and out preferentially in only one direction. So that's the other kind of metal semiconductor contact. So maybe later in the semester when we talk about advanced transistor structures, a lot of you had asked, let's say, about carbon or carbon nanotube. People are starting to do research on two-dimensional semiconductor materials to make advanced transistors. And it turns out that the performance of these advanced transistor structures is often limited by the metal semiconductor contact. And so it's important for you to understand why. I'll tell you right now, you might remember it later, that for some of the advanced semiconductor materials, it's not easy to dope the semiconductor to make it electrically very conductive right at the metal contact. And for that reason, you have very large resistance to current flow across that interface. So even if you have a very high performance transistor material, if you can't get the current in and out effectively without wasting a lot of voltage dropped across the contacts, then you're not going to get the performance you want from the high mobility channel materials. Okay, so that's why it is actually fundamentally very important to understand metal semiconductor contacts. So there are two classes of semiconductor contacts. Okay, one class is rectifying. So rectifying just means that if you look at the current versus the voltage dropped between the metal and the semiconductor, it actually allows very little current to flow in one direction. So like if you apply, let's say, a negative voltage, for example, this applied bias, let's say we have, now this is just a lateral cross-section. Let's say we have a metal here and a silicon here, and we're trying to apply a voltage across this two-terminal device. The resulting current that flows like this, well, if the voltage applied bias is negative, then very little negative current flows. And only if the applied bias is positive, that is, more positive voltage on a metal compared to the semiconductor, a significant amount of current can flow, exponentially increasing. So this is an example of a rectifying IV current versus voltage characteristic. And this kind of a metal semiconductor contact is usually called a Schottky contact or a Schottky diode. Okay, diode means it's like two terminals, and it preferentially allows current to flow in one direction. Okay? So for allowing current to flow easily into and out of this transistor, you actually need metal to, the current to flow easily from the metal to the semiconductor as well as from the semiconductor to the metal. So clearly a Schottky contact is not what you would like to have in this particular application. So what you'd like to have is a non-rectifying current versus voltage characteristic if you're just trying to get metal interconnects connected to the transistor. So an ohmic contact is the other extreme, where current roughly looks like a linear function of the applied bias. Okay? And it flows easily in both directions. Right? So if you apply a negative voltage, you can have a lot of negative current flow. If you apply a positive bias, a lot of positive current flows. And so the slope here is the change in current over the change in voltage. So it's basically, you can call it 1 over the contact resistance, right? 1 over the contact resistance. Okay, that's the inverse. So this contact resistance is the inverse slope. So in other words, ideally for a metal semiconductor contact, if you just want to flow current into and out of the semiconductor, you'd like this curve to be as steep as possible. In other words, you don't really want to apply a lot of voltage across the contact in order for a significant amount of current to flow. Yes?
The integral of that is the formula? Is that what that phrase?
Oh, sorry. The integral. No. So the change in current divided by the change in voltage.
What's the thing directly to the left of that?
That is just, oh, that's a slope. Sorry. That's to denote the slope. Right? Okay. Sorry about that. Okay. So those are the two types of contacts we'll cover today. All right. So the key, just qualitatively, what we're going to go over is that in one case, the majority carrier in the semiconductor can easily move into and out of the metal. Okay, that's the ohmic contact, sort of following Ohm's law, right? The change in current is going to be directly proportional to change in voltage, and the proportionality constant is related to the contact resistance. So carriers that if the carriers can move easily into and out of the metal, then you have an ohmic contact. If the carriers only can easily flow in one direction, then you have a rectifying or Schottky contact. Okay, so we're going to see why that's the case. So to understand this, then we need to review one other basic property of any material, and that is the work function. Okay, so the work function is simply defined to be the minimum energy needed to remove an electron from a solid. And technically, it's just to remove it into the vacuum right beyond the surface of the solid. Okay? So just bottom line, just think of it. How much energy does it take to remove an electron on average from the solid? Okay? So for a metal, the way we draw an energy band diagram for a metal, remember there is no band gap, energy band gap in a metal. So you have in the energy range of interest, you have a continuum of allowed energy states which electrons can occupy. But the electrons, due to thermal, they have a thermal distribution, they'll occupy most of the states below the Fermi level, and they will not occupy most of the states above the Fermi level. Okay? So let's review. we plot the Fermi function as a function. No, let's do it this way. Let's plot on the vertical axis energy, and the horizontal axis the Fermi function. Maybe I'll do it on the screen so in case people watch this on the webcast, they'll get it. So let's just draw this. So this is energy, and let's say the reference energy is the Fermi level, and we're plotting the magnitude of, the probability of occupancy of an allowed energy state. So I'm just going to sort of exaggerate the slope here. So it's kind of relatively high temperature. So at the Fermi level, the probability of a state being occupied is 1/2, and if the energy level is well below the Fermi level, then probability of occupancy is 1. Okay. So just to remind you, then, this Fermi distribution does hold for occupancy of allowed energy states in the metal. Okay. So basically, states that are energy levels that are slightly below the Fermi level have some reasonable chance of being empty because the electrons from those energy states had enough thermal energy to go up to higher energy. So I guess bottom line is there's a reasonable probability of finding electrons within a few kT, right, within just a few kT of the Fermi level in the metal. Does that make sense? And there's a reasonable probability that there are holes. Well, if you imagine that there might be holes in a metal, there's a reasonable probability of having holes at energy levels within a few kT of the Fermi level in the metal. So this is like a few, let's say 3, or let's say within 5 kT, right? There's some reasonable chance of occupancy of finding holes, and within a few kT up here, let's say about 5 kT, you have some reasonable probability of finding electrons. Okay. All right. So now let's go back and look at the Fermi, the energy band diagram for a metal. So the Fermi level just denotes, okay, that's the level, energy level, where the probability of occupancy is 1/2. So we know that slightly below that Fermi level, there's a significant number of holes, and slightly above that Fermi level, there's a significant number of electrons that you can find within the metal. Okay? So that's the energy band diagram on the left for a metal. And the work function, okay, so the work function, the symbol for work function in this class that we'll use is capital phi. Okay? And the units are that we're going to use are electron volts. Okay? Units of energy are electron volts. Okay, so phi sub m means the work function of the metal, and phi sub s denotes the work function of the semiconductor that you're contacting. Okay? All right, so the free electron energy level, so that's the vacuum energy level, E0 is shown for reference here. Okay, so the work function phi sub m hopefully is clear. So the average energy it takes to remove an electron from the metal is just the difference between the vacuum energy level and the average energy level of an electron. Yes, Ali? Order of magnitude. Good question. So the phi sub m is actually on a later slide. For most practical metals, phi sub m is somewhere between 4 and 5 electron volts, roughly in that range. Okay? Good question, because that's going to be determining if it's a rectifying or a ohmic contact. Okay, what about silicon? Well, silicon is kind of a little bit different because we know that electrons really cannot exist within the energy band gap. They only exist out here in the conduction band or valence band. So the work function is defined, as shown here, is defined, phi s is defined to be the free electron energy level, the vacuum energy level, minus the Fermi level, right? The difference between those two. Okay. Here's a new quantity here. That's chi is the electron affinity. And in silicon, it's 4.05 electron volts, and in silicon at room temperature. Okay, so that's chi. The work function is defined to be the vacuum energy level minus the Fermi level. Okay, so that's the same for the metal as for the semiconductor. Okay, so this is equal to E naught minus EC. Yeah, that's just a definition. What does that describe? So the electron affinity, that's kind of, well, that's like how attractive a semiconductor's conduction band is to an electron to occupy. Because most electrons, are occupying it allowed energy state very close to the conduction band edge. So basically, if that difference between the vacuum level and the conduction band is large, then it's a deeper kind of energy well for an electron to go into. So basically, an electron would like to go into a material with larger electron affinity. I guess that's why they call it electron affinity, right? How much it likes to hold electrons. Okay, so if you look at this energy band diagram, you can see that phi sub s is just equal to chi plus EC minus EV. So the work function of the metal is a fundamental property of the material. So if you look up on Wikipedia, properties of various metal elements, they'll give you the work function value. For a semiconductor, the work function depends on the dopant concentration, right? Because this Fermi level depends on the carrier concentration, which depends on the dopant concentration. Oh, shoot, I'm sorry. Yes, you're right. This is a type, thank you. EC minus EFS, right? So the difference between, right, the difference between the conduction band and the Fermi level in the semiconductor. That's right. Sorry about that. Thanks. Okay, so EC minus EF, that is determined by the electron concentration, which is dictated by the dopant, the net dopant concentration. Okay. So remember then, the work function is this is a fundamental property of the material. So in an energy band diagram, the work function and actually the electron affinity is going to be the same, no matter which part of the semiconductor you're looking at. Okay, so that's constant. Okay, so that's the new thing we have to sort of introduce before talking about the energy band diagram for a metal semiconductor contact. Okay, so let's see what happens. So there's 4 combinations. This metal to N-type semiconductor, where the work function of the metal is less than that of the semiconductor. And then there's contact to N-type semiconductor, where the work function is greater than the work function of the semiconductor. And then we can do the same thing for P-type. So there's 4 different possible combinations here. Okay, so let's look at the first situation of a metal contacting an N-type semiconductor. So you can see that the Fermi level is, in the semiconductor is close to the conduction band edge. Okay, so let's just imagine we put the metal into contact with the semiconductor, and immediately after contact, before any electrons move around, the energy bands will line up like this. Okay, because the vacuum energy level should be continuous in any system, and so basically end up with this energy band diagram immediately after contact. Okay, does everybody sort of see that? Okay, so just qualitatively, if the work function of the metal is smaller than the work function of the semiconductor, in other words, the Fermi level is higher. Is that right? Did I draw this? Oh yeah. Well, so it's easier to remove electrons from the metal than it is to remove electrons from the semiconductor. Which direction do you think electrons are going to want to flow when the two materials touch? Semiconductor, that's right, because it's just the average, the Fermi level actually determines the electrochemical potential of electrons. So if the Fermi level is lower starting out on the semiconductor side, electrons will want to go over to the side where they have lower electrochemical potential. So electrons, right after touching, electrons will want to go to the right, okay? But what will happen when they go to the right? Yes, Andrew. So up there at the top, this is not thermal equilibrium. At the bottom is the equilibrium band diagram. So in equilibrium, so remember, if I ever ask you to draw an equilibrium energy band diagram, the first thing you should do is draw EF as a horizontal line. It's the same all throughout the device. Okay, so in equilibrium, the Fermi level is at the same level in the metal and in the semiconductor. So that means that there must be some like energy band bending in this region at the junction. Okay, so if electrons moved from the metal into the semiconductor, because there was, it's just more favorable, lower electrochemical potential to go into the semiconductor, then the surface will become more n-type. Right? So notice the conduction band edge gets closer to the Fermi level in the semiconductor at the junction. Yes, question. That's a good question. Do the electrons go to the conduction band or valence band? Yes. Okay, so that's why I went over this Fermi distribution earlier, because even though the Fermi level in the metal is lower than the conduction band edge, there's still, okay, so usually when this happens, okay, typically when this happens, with any practical metal material, this difference is on the order of on the order of 1/10 of an electron volt. So basically, that there will be plenty of electrons at this energy level up here to be able to move easily into the conduction band. Okay, yeah, that's why I sort of reviewed the Fermi distribution. Okay, so the answer to your question is that they actually mostly move into the conduction band because there are very few holes in an n-type material. Very few holes means that actually most of these are filled already, right? So basically most of the states in the valence band are filled. So the only place for electrons to go really are mainly in the conduction band. That's a good question, though. Yes?
At equilibrium, is it true to say that the work function is more?
Is it fair to say that work function is equal? That's absolutely right. So bottom line is the total amount of energy band bending in the silicon is ideally equal to the difference in work functions. You're absolutely right. So basically, you're trying to just compensate for that difference in work function. So that's exactly right, because the Fermi level ends up at the same level. Starting out, the work functions were different. So of course, the total amount of energy band bending has to exactly cancel out the difference in work function. Okay, so looking at this energy band diagram, hopefully you can see that it's possible for electrons to move, only because this barrier height is relatively small. Electrons can move easily into the semiconductor. Certainly electrons can, in the conduction band, if we apply an electric field, can easily move into the metal. So this is a ohmic contact. Okay, ohmic contact to n-type material. So this current versus voltage characteristic will look ideally almost like a straight line like this. Okay. So I wanted to just remind you. So the convention we use in pair A is that the applied bias is always defined to be the voltage applied to the metal minus the voltage applied to the semiconductor. So the semiconductor always serves as the reference potential. Okay. So this is. Okay, so, well, the other case must be the rectifying contact, right? So if the work function of the metal, okay, right, again, immediately after they touch, the work function of the metal now is larger than the work function of the silicon, right? So this distance here is smaller than the distance here. So when the materials touch, electrons will tend to want to, because they start out at higher electrochemical potential, they'll tend to want to go into the metal. Okay? So when electrons leave an n-type material, what do they leave behind? Positive charge, right? Electrons are negative. So the semiconductor starts out charge neutral. You have electrons, but you also have ionized donors, right? When electrons leave, all you have left are ionized donors left behind. So you leave behind positive charge when the electrons leave. So electrons, because of the difference in work function, move into the metal. They leave behind positive charge. And due to Poisson's equation or Gauss's law, basically you end up with, I'll just write down here, you end up with like positive ionized donors left behind in the semiconductor, and you have like electrons sort of that went into the metal. Okay, so you have some electric field that results from this. So you have some electric field this way. Okay. For this electric field, which direction is that electric field causing electrons to drift? To the right. And that's okay. Sorry about that. All right, so an electric field is built up because electrons leave and leaving behind positive ionized donors. And so electric field is built up to counteract, to basically prevent any more diffusion after some point. So under equilibrium, you do have electrons going to the left and to the right, but there's no net motion of carriers across that junction. Okay? And as somebody pointed out, that this total band bending that results in the semiconductor is actually exactly the amount of band bending to compensate for the difference in the work functions to begin with. Yes, question?
So what happens is the electrons.
That's right. That's right. Right. The electric field builds up, so the drift current now balances the diffusion current. Okay. Okay. So let's see. I think this is usually tricky for people to see. So one piece of information. Okay. There's something that we skip. So usually when we draw the energy band diagram for a metal semiconductor contact, we don't bother to draw the free electron energy level because it really doesn't affect anything. But let me just draw it here just once for you to see. So it's going to look something like, it's basically just going to follow. So this distance here is the work function of the metal. And this distance here is the electron affinity of the semiconductor, chi. And remember, chi, the electron affinity is a property of the semiconductor. So chi is constant throughout the semiconductor. So E naught has to be, this fixed distance above the conduction band edge. Okay? Now, in this particular case, we have a significant, typically when we have this kind of a situation, there's a significant barrier now to electrons diffusing to the right from metal into the semiconductor. So this barrier to electrons, which is why it's called phi sub b sub n for negatively charged carriers. So phi sub b sub n, that's defined to be the Schottky barrier height for electrons. Okay? And from this energy band diagram, hopefully you can see that phi sub b sub n is equal to the metal work function minus electron affinity, ideally. Okay? Now what about this total band bending within the semiconductor? As I mentioned, it actually is exactly equal to, ideally, to the difference between the metal work function and the semiconductor work function. That has to be the case in order for the Fermi levels in these two materials to actually end up at the same location. So let's see. So the easiest way to calculate this total amount of energy band bending within the silicon is to look at the Schottky barrier height and subtract EC minus EF in far away from the junction. Okay, so that's basically FB stands for flat band. Uh-oh. My pen. Or flat band. Okay, so this means EC minus EF where the energy bands are not bending anymore. Okay, so way out here where the energy bands are not bending, take the value of EC minus EF there, subtract it from the Schottky barrier height, and that will give you this total amount of energy band bending in the silicon, which is defined to be the built-in potential, VBI. Okay, so VBI is defined to be the so-called built-in potential. So this is the electric potential that is needed to exactly counteract a diffusion current, right, to balance the diffusion current. So in equilibrium, you don't have any net current flow across the junction. Yes?
What's causing this?
Energy required to be.
So I mean, the band bent. So I mean.
On the previous slide, it bent downwards.
No,
Oh, okay, up here?
yeah, from the top to the bottom, you bent because you have phi.
Hi, yes.
Right.
Uh-huh.
So that would be the same thing as the convective band on the first one.
Yes.
What caused the energy reduction?
Okay, so the reason why the bands come down is because in equilibrium, the Fermi levels have to equilibrate to the same level, okay? And in order for that to happen, you actually have to build up charge in the semiconductor to make it attractive for, I mean, basically to have this electric field to start to attract electrons back to, so the electric field is helping to induce a drift current going to the right of electrons, right? Electrons going to the right, but the electrons naturally also want to diffuse to the left, and you want to balance it out. So you have some charge in the semiconductor, right? Ionized dopants that are left behind have this electric field, and remember from Poisson's equation, Poisson's equation, if you have charge, if there's non-zero charge density, that means there's electric field there, and there therefore is a voltage drop. Okay, so there's a voltage drop that sort of is, you think of it as like building up a potential barrier, like raising a potential barrier to prevent electrons from diffusing. Okay, so that's one way to think of it. See, normally right after contact, you see electrons, they easily just spill from the conduction band into the metal, right, because the Fermi level's lower there. But now over time, you build up a potential barrier to prevent that from happening, to hold it back. So in equilibrium, there's no net loss or gain of electrons in the semiconductor. Yeah. So it's like raising up like the floor, so it's harder for electrons to go over it. Yes?
In the ohmic,
That's right. The Fermi levels are equal.
and the Schottky one is not equal.
Well, the Fermi levels are always equal. The work function is not necessarily, the work function is not equal, right? Because oops, let me draw. That's a good question. So one thing that was missing here also is the E naught, right? So E naught is up here, like this, right? So the work function for the metal is still different than the work function for the semiconductor. Right? So we're not equilibrating the work functions, we're just compensating for the work functions by having a built-in voltage developed right at in the semiconductor. Does that make sense? Okay, good question. Yeah, sorry.
Sorry, I thought the reason why the Schottky one wasn't able to go back.
Okay, so that's a good question. So here, in practice, this barrier to electrons flowing, there really is this really small, this so-called barrier to electrons flowing from the metal to the semiconductor is small, such that it's within a 1/10 of a electron volt. So there's still plenty of electrons that have enough thermal energy to get, flow into the semiconductor. Once that barrier gets too large, then yeah, it might not be perfectly ohmic anymore.
So you're saying the vacuum level changes.
Yeah, so the question is, okay, we're changing the vacuum energy level. The only requirement is that the vacuum energy level has to be continuous. It doesn't have to be the same, like in one part of the system as the other, but locally it has to be a continuous function of the distance. So that is the reason why the E0 looks like this. It has, oops, what happened? Okay, somehow I accidentally erased that. But anyway, yeah, so E0 has to be a continuous function of distance. Okay, so yeah. Does that make sense? Because you're absolutely right. Locally, it doesn't make sense. Like just to the left or just to the right, it's not going to be any easier to remove the electron from that material. So it has to be a continuous function of distance. Okay, so that's basically. Okay, that's a Schottky barrier, Schottky contact. Okay, so the reason, just qualitatively, before we go, so next time we'll derive the current equation. But basically, because of this large barrier to electrons diffusing into the semiconductor, it is very difficult to get electrons to move to the right. Okay, so in other words, you won't get much current flowing. Let's see, electrons moving to the right. So that's negative current. So you won't get much negative current flowing in this device. Okay, so if you apply negative bias, you won't be able to get much negative current to flow. But if you apply a positive voltage to the device, what that will do is it can change the total voltage drop in the semiconductor. So you can change this, you can reduce this built-in potential to carriers diffusing to the left. So if you apply a positive voltage, you'll end up reducing that barrier and allowing exponentially more and more electrons to be able to diffuse to the left. Okay, so electrons diffusing to the left is just positive current flow. So this is basically a rectifying contact. Just qualitatively, that's what's going to happen here. Yes, Ali?
So is the barrier height, is that the breakdown?
Okay, so how does this relate to the breakdown voltage? The breakdown voltage for the structure is let's see. Okay, so in a Schottky contact, I don't think we never talk about a breakdown voltage. Okay, later when we talk about p-n junctions, breakdown can occur through one of multiple mechanisms. What can happen is that you can apply a large negative. Okay, so as I said, if you apply a positive voltage, you can actually reduce this barrier. If you apply a negative voltage, you actually make the barrier to electrons moving to the left even higher. So the only current that can flow is electrons moving to the right, but then that's really not much current because of this large barrier. If you move these energy band diagrams on the energy band on the right down too much, you could potentially get some quantum mechanical tunneling of electrons from the metal into the semiconductor because this barrier becomes physically very narrow. Okay, so that could be considered like some kind of a breakdown characteristic. But and the voltage at which that quote tunneling occurs would depend on that barrier height. That's true. Yeah. Okay. Now in reality, We never have a pristine interface between a metal and a semiconductor. There's always going to be some dangling bonds or some, in a metal you have all these allowed energy levels that can be occupied, and then suddenly you see the semiconductor and there's an energy band gap. So there's like no allowed energy levels in this range within the band gap. So you'll have, therefore, some evanescent sort of states, allowed energy states right at that interface located within the energy band gap. So what that means is that depending on the Fermi level, okay, some of those allowed energy levels within the band gap at the interface are occupied by electrons. So in other words, there's always going to be some charge at the interface between a metal and a semiconductor. And so you can end up with a dipole, okay, electronic dipole, plus or minus or plus, depending on the materials. So in practice, what that dipole does is it modifies the Schottky barrier. So in practice, even though I mentioned, okay, ideally, the Schottky barrier is just going to be dependent on the work function of the metal and the electron affinity. In practice, that equation is never the case. You have to experimentally measure it. Okay, and so basically people tabulate experimentally measured values of the Schottky barrier height for various metals contacting with silicon. Okay, so basically, right at the interface you have some slight, due to the dipole, you can have some shift in the energy band to change the Schottky barrier height. Okay? Yes, question? Is this similar? Okay, so the band bending in the semiconductor is similar to depletion region in a PN junction. So you're absolutely right. The reason why we have that energy band diagram, energy band bending, is because the surface region close to the metal is depleted of electrons. And electrons, upon contact, they really prefer to be in the metal. So the surface region is depleted of electrons, and we'll come back to that. And so you have charge there due to the. Okay, the question is about that dipole. That's just it's not a depletion region. It's basically just suddenly a discontinuity essentially.
The vertical line, the second vertical line, does that have any
Talking about this here.
Yeah, the spacing between them as far as the distance. Does that have
Okay. Well, technically, if we're still talking about being right inside the semiconductor, then there's still some kind of a band gap. Okay, so remember, okay, I'm just going to review. So we have, from Poisson's equation, we have the charge density distribution. If we know the total charge in a semiconductor as a function of distance, then that can give us the electric field as a function of distance, and that can give us the voltage drop as a, the electric potential as a function of distance, and that gives you, EC as a function of distance. Okay, so what I'm saying is that there's charge, just like a delta function of charge, right at that interface. And so if you have, then you can have an abrupt change in electric field, and therefore some voltage drop right at the interface, and that gives, then you have, that's reflected in the EC as a function of distance. So essentially, the separation between these two, you still have this band, it's still silicon, so you have the band gap. But now the band bending is just following, is dictated by this charge density at the interface. From that, you see the change in the field voltage, and therefore E sub C.
Right, but the difference between like that plus and the minus doesn't have any intrinsic.
Well, in this particular example, okay, there are allowed energy levels in the band gap. And so let's see, we have a Fermi level here. So basically what's saying that, let's say we have some trap states, not traps, well, yeah, allowed energy states right here within the band gap. And anything, remember, any allowed energy levels right at the interface below the Fermi level are occupied. So they're going to be negatively charged. And so there will be a dipole, sort of positive on the metal side, negative on the semiconductor side. So remember, electric field, okay, it was going to be pointing at, this dipole is going to give rise to some small, increment of electric field pointing to the right. So that's why the energy bands are sloped upwards like that. Yeah, sure. So bottom line is phi Bn, this Schottky barrier height, is actually lower than what is ideal, you would ideally calculate, right? Because it's like making the energy bands diagram go down to the left. Okay, so basically for the homework and for exams, if I give you the numbers, just use these values for phi Bn, and actually for the whole Schottky barriers, I'll define in the next slides. But basically, just remember you should use the real experimentally measured values of the Schottky barrier heights for electrons here. So these are for some metals that have been used to contact silicon. So most, okay. So tungsten, for example, was used for quite a while to contact silicon. But it turns out that in a semiconductor fabrication process, for various reasons, when you deposit films like of dielectric and metal and so on, you have to heat up the wafer to fairly high temperatures, well, a few hundred degrees Celsius, let's say. So if you have a metal contacting silicon, you actually react the metal and the silicon. So a compound of metal and silicon is called a silicide. So in practice, these source and drain regions are contacted. Electrical contact is made by reacting metal with the semiconductor to form silicide. And the most common silicides used today are nickel silicide, and in the past, when I was a student, so that's like 30 years ago, tungsten silicide, and in between it was titanium. But today it's primarily nickel silicide. Okay, so for the homework that's being assigned today, you'll look at Schottky contact for silicide, nickel silicide contact to silicon. Yes, Andrew. Okay, that's a good question. So the question was, what if you just use a degenerately doped semiconductor? That is quite possible. So degenerately doped, let's say, N-type silicon, like polycrystalline silicon. So if you deposit silicon as a electrical interconnect material, it has to go over, you deposit over like dielectric materials that are amorphous. So they don't have any crystalline structure. So when you deposit silicon just on a random surface, it's not going to be a single crystal, right? It's going to be polycrystalline. So you can use very heavily doped polycrystalline thin films of silicon to form electrical interconnects locally, like from one transistor to another. And that used to be done in the decades ago. But these chips, they might be millimeters or centimeters across. And if you remember from one of the previous lectures, so resistance is going to be equal to the resistivity times the length divided by the cross-sectional area. Typically, the thin films of interconnects are less than a micron thick. Okay, it costs too much to deposit something much thicker than that. So less than 1 micron thick, and the width of these interconnects are also less than 1 micron wide, typically. So that's like the cross-sectional area of 10 to the minus 8 square centimeters. The length can easily run, millimeters. Okay, so that's like 10 to the minus 10 to the minus 1 centimeters. And what's the typical resistivity of very heavily doped silicon? A very, very heavily doped silicon maybe is on the order of 1 milliohm centimeter. Okay, so let's say if you want a millimeter long interconnect, and the cross-sectional area is 1 square micron, 10 to the 7. So basically that's 10,000 kilo ohm. Yeah, 10,000 ohms, right, for the interconnect. So basically, if you are conducting current, like a milliamps or an amp of current, well, not an amp, but say a milliamps of current, you'll get significant voltage just wasted, just dropping across your interconnect. So for that reason, we would prefer to use metals which have resistivities more like 1 micro ohm centimeter, so 1,000 times lower. Right? So you really don't want interconnects to have significant resistance compared to your transistors when they're on.
So is silicide a metal?
Okay, so the question is silicide a metal or semiconductor? A silicide is, you can think of it as a metal for the purpose of looking at metal semiconductor contacts. Okay, so now let's look at the energy band diagram, and let's figure out, okay, how wide is that region that's depleted of electrons? Okay, so to understand this qualitatively, let's make use of a very simple approximation called the depletion approximation. So it's basically summarized down here. What we assume in a depletion approximation is that the semiconductor is depleted to a certain depth, let's say x sub n. Okay, so that's the distance x, n for sub n for n-type. So let's just assume that all the electrons have diffused over to the metal, and so you only have ionized donors left behind. So there's a charge density, it's positive, right? The donors are positively charged. So it's Q times ND. That's the density of coulombs. So coulombs per centimeter cubed. That's the level of charge in the semiconductor. And let's just assume that the electrons have pretty much all gone away, disappeared to metal, down to a distance W away from the interface. Okay, so basically when the metal and semiconductor came into contact, electrons left, and so just some thin or narrow width of the semiconductor is now completely depleted of electrons. So the depletion approximation is just saying n is equal to 0, and let's just say, because it's a minority carrier, p equals 0 in the depleted region. Okay, so the of width, let's call it W. Okay, so within this depleted region, so from x equals 0 to x equals W, the charge density per unit, the charge density is just coulombs per centimeter cubed. It's just given by the net dopant concentration. Okay, so this is what we covered at the end of the last lecture. Okay, so donors are positively charged. If there are any acceptors in the background, they're negatively charged. You have to subtract that out. Okay. So here, n equals 0, and to the right, n is going to be equal to nd. So this is clearly an approximation, right? That the electron concentration is just the normal equilibrium concentration, beyond the depletion depth. But within the depleted region, n is 0. It's just an approximation. Okay, so in other words, if n equals nd, the charge density is 0 outside of the depletion region. So we call this region near the surface the depleted region, and we call this region here the neutral. So it's a charge neutral region. That make sense? Okay, so when electrons moved to the metal, there's an electric field that's built up, right? You have positive charge on the right due to the ionized donors, and then you have negative charge on the left due to to electrons. And so electrons, this is a metal, so electrons will tend to stay at the surface of the metal, right? So it'll be a negative charge, a large negative charge right at the interface inside the metal. And the total integrated charge, so the amount of negative charge in the metal has to equal the amount of positive charge in the semiconductor. Okay? Okay, so now let's use Poisson's equation. We have the charge density as a function of distance. Okay, it's just constant in this depleted region. And let's just assume it's doped with donors only, so there's no acceptors to worry about. Okay? So basically what we're going to do is we're going to use Poisson's, this is a big picture, Poisson's equation to go from the charge density as a function of distance, right? So we now know the charge, due to the depletion approximation, we have charge as a function of distance. We're going to therefore use Poisson's equation to get the electric field as a function of distance. From that, you can get the electrostatic potential V. And graphically, you can see that here. So charge density is a constant as a function of distance. And when you integrate, okay, so the electric field is the integral of charge density. okay, is a constant. Sorry, since charge density is a constant, then the solution is just AX plus B, right? Where A and B are constants. And the boundary conditions. Boundary conditions. At 0, okay, the electric field strength at 0 and the electric field strength at W. Okay, the easy one of these is probably at W, right? Electric field strength, in a neutral material, we know that this has to be, there's no reason why an electric field should exist in a neutral material. So we know the electric field has to go to 0 in the neutral region. At the interface, it's going to reach a maximum. Okay, so if you look at this equation for charge density, hopefully you can see that's equal to this. Because we're integrating, I mean, it's increasing, the electric field strength should be increasing going to the left, increasing going to in the negative x direction. Okay, so we have positive charge here, negative charge here. So we know the electric field has to be pointing to the left, right? It's negative. Okay. So we just integrate the charge from x equals W to x equals 0, and you can get the peak electric field at the interface. So with these two boundary conditions, you can solve for A and B, and you'll find that electric field is just a linear function of distance. So hopefully qualitatively this makes sense. You integrate a constant function of distance, and you get a linear function. And then you can integrate again, right, the electrostatic potential you obtain by integrating the electric field distribution. It's a linearly increasing negative function, so it's a quadratic function of distance. And you know that the total voltage drop is just defined to be the built-in potential. So the built-in potential is the magnitude of this voltage drop in the silicon. Okay? So just to remind you, the relationship between electric field and voltage is just the change in voltage over distance is given by gives you the electric field. So let me just write this in. So it's plus Q N D epsilon S times W minus X dx. So this is just a simple integral of a linear function. Okay, so you know, electrostatic potential is all relative. So notice that we're sort of arbitrarily choosing the electrostatic potential at x equals W to be equal to 0, right? Remember I mentioned we're always choosing the silicon as a reference voltage level, so that's 0. Okay, so that's what I mean. We're assuming the voltage at the semiconductor, you know, far away from the junction is 0, and you'll have, therefore the voltage right at the junction is minus VBI. Okay? Just to make it absolutely clear, the slope here is equal to the change in electric field versus distance, and so that's equal to QND epsilon S, right? That's the Poisson equation. Okay, so there's a positive slope because the charge in the semiconductor is positive. Okay, qualitatively, does anybody have questions about this? Yes.
Quickly, DE or what?
DE dx. Yeah, that's Poisson's equation. Okay, so let's solve for the depletion width then. So this is just the equation on the previous slide again. Oh, and I forgot to mention last time. So this relative permittivity is 11.7 for silicon. We'll use that value here. But actually, what you should really remember is that the permittivity of silicon, the dielectric permittivity for silicon, is 10 to the minus 12 farads per centimeter. That's easier to remember, I hope. Okay, so for the quizzes, I'm just going to tell you to use permittivity of silicon is 10 to the minus 12 farads per centimeter. Okay, so if you plug in x is 0 and set the voltage to be equal which is defined to be the built-in potential, then you can find an expression for W, the depletion width. Okay? So the width to which you're depleting the silicon is going to be proportional to the square root of the built-in potential. Right? So the total voltage drop in the semiconductor is going to determine the depletion width. So if you have a wider depletion width, well, if you need a wider depletion width to drop more voltage. Okay? And the reason for that is because the area, just to graphically, the area, what does this area represent? Yeah, the area is the total voltage drop across the silicon, right? So if you want to drop more voltage, like let's say the difference in work function was greater, so that means you have to have more built-in potential to equilibrate the currents flowing in to the left and right. If you have a larger difference in work function, you have a larger built-in potential that you need to build up to counteract diffusion. That means you need a larger area underneath this E versus X curve. How do you increase the area underneath a triangle? Given that this slope is fixed, right? Because this slope is, like I said, the slope in the change in the electric field versus distance, that's set by Poisson's equation, right? Yeah, right. So that's rho over epsilon s, right? So the dopant concentration is constant as a function of distance, so this slope is constant. So if you want to change the total voltage dropped for a given dopant level, you have to basically change the width of the depletion region. So like if you want to increase it, you have to increase the depletion width so the total area under that curve increases, right? Because you can't change the slope. The slope is set by the charge density. Okay, well, what about so what about increasing n sub d? Qualitatively on this E versus X plot, okay, let's do that. How would the charge density plot change if we increase n sub d? Oh, okay, like this one up here, the very first plot. Yep, the doping concentration goes higher. Yes, so actually I drew it wrong. It'll be like this. Okay, because the built-in potential will change a little bit because the Fermi level is going to be different if you have higher doping. Okay, so you're absolutely right. If we have higher ND, then the charge density will be higher. Okay, and so the slope will be steeper. Okay, so the slope will be steeper, and depending on the exact doping, basically. So this area, this area will be slightly larger because the total, the difference in work function will be slightly larger. Okay, but this is one way. Okay, so the depletion width, this width can be narrower if you increase the doping. I mean, it will be narrower if you look at this equation, right? So if you increase the dopant concentration, the slope of this E versus X curve gets steeper. So you don't need to have as deep of a depletion width to drop the, about 1 volt of voltage. Does that make sense? Okay. So this form is important for you to remember, but this is not the actual equation you should memorize. And let me explain why. Because when we now use a metal semiconductor contact, we always are curious how current flows as a function of applied bias. So let's see what happens then when you apply a voltage across this device. It turns out that what happens is that you're applying metal silicon, let's say doped silicon, right? So typically, whenever we make a metal semiconductor contact, it's like a moderately doped semiconductor. So let's say we apply a bias across this device, like this, or maybe not. I guess the question is, where is the voltage dropped? Okay. I'll just change color by accident, but anyway, okay, there we go. So you have some voltage difference between the metal and the semiconductor that's applied. That's equal to VA. All right. So where is that voltage really going to appear within this structure? Well, metal is electric. Okay, so you have voltage applied and therefore some current that flows. But you can model this as different regions. So each of these regions has some resistance, right? So the metal has some resistance. That depletion region has some effective resistance to current flow. And the doped silicon has some resistance to current flow. Okay, so you can sort of model this metal semiconductor system as like resistors in series, right? You have the same current flowing through the structure. The metal should be less resistive. The doped semiconductor is less resistive. The depletion region, having very few mobile charges, is going to be the most resistive part of this structure, right? So from EE130, when you flow current, the same current through series connected resistors, where is most of the voltage going to be dropped? The largest resistor, right? So most of the voltage will be dropped across the largest resistor. So ideally then, for this class, we're just going to say, okay, if we apply a voltage to this device, it's just going to appear across the depletion region. Okay, negligible voltage will be dropped in the semiconductor, in the dope region, and negligible amount of voltage dropped in the metal. Okay? So let's look at the applied bias, VA. Remember, the built-in electric field is pointing in this direction. So this applied bias is counteracting that built-in electric field, right? So if VA is positive, then basically you're counteracting that built-in electric field. You're reducing it. So notice then that this total amount of this potential barrier to carrier diffusion to the left is reduced. So it's going to be your built-in potential minus VA. Make sense? So when you apply a positive bias, that bias appears across the depletion region, and it counteracts that built-in field. The total amount of voltage drop in the semiconductor reduced. So remember from the last homework, the concentration of electrons that have enough energy to surmount that barrier, basically the shorter the barrier is, the shallower the barrier is, exponentially have more and more electrons that can make it over the barrier. Right? Remember the distribution of electrons in the conduction band? It's like an exponentially decaying tail. So only the electrons that have kinetic energy greater than that potential barrier are going to be able to diffuse to the left. Okay? So by reducing the potential barrier linearly, you're increasing the number of electrons that can diffuse to the left exponentially. And that's why the current increases for forward bias exponentially. Okay? Now, how about for reverse bias? If this is for VA greater than 0, for VA less than 0, okay, so now you're applying some negative voltage here and positive voltage here. That's sort of reinforcing the built-in electric field. You're going to increase the total amount of voltage dropped in the semiconductor. Okay, so this distance here is again Q times VBI minus VA, but now VA is negative, right? So the total barrier height to electrons diffusing to the left has been increased. So this arrow coming back like this means that, okay, basically negligible number of electrons now can diffuse to the left. The only electrons that are flowing across the junction are those which can surmount the Schottky barrier height flowing from the metal into the semiconductor, and that's just some small negative current. Okay? Qualitatively, does this make sense? So one thing, what's happening to the width of the depletion region here? It's changing, okay? Right, so if you only need to drop a small amount of voltage in the semiconductor, then you don't need as much depletion charge, so the width of the depletion region goes down. If you need to drop a larger voltage, you have to increase the depletion width. So again, this is because the dopant concentration in the semiconductor determines the slope of electric field versus X. Right? So this slope is determined by is fixed by the dopant. So when you change the voltage applied to your metal semiconductor junction, you're not changing the doping. So you're not changing the charge density in the depletion region. So the only way you can change the total voltage dropped across the semiconductor is to change the width of that depletion region, to change the total voltage drop. Okay, because the slope of this curve has to stay the same. So basically the width of the depletion region changes as you change the applied bias to change the total amount of voltage dropped across the depletion region. Okay, so qualitatively we can rederive this, but remember the equation earlier, the depletion width is proportional to the square root of the built-in potential, but it's really the square root of the total voltage dropped across the silicon. So now that's VBI minus VA for the more general case. Okay, so it's the exact same equation as before, but now it's the total voltage dropped across the semiconductor in the general case is VBI minus VA. Okay? Any questions qualitatively about this? Yes, Bjorn. How good is that approximation? It's good to understand qualitatively what's going on in the metal semiconductor contact. But if you really want to have an accurate, a more accurate calculation, this is when you want to use computer software simulation programs where you actually keep track of dopant concentration, because the dopant profiles might not be constant as a function of distance and so on. So the software simulation programs do keep track of real charge density as a function of location, and it keeps track of diffusion and drift currents, and it keeps track of continuity equations. So you can solve it more precisely. But actually, this is not a bad approximation at all. Okay, so finally, the final topic here is that, okay, so there's actually some charge stored in the semiconductor. So let's think about this. As I mentioned, when you change the applied bias, you're changing the width of the depletion region. So you're changing the amount of charge on both sides of this junction. So we consider this to be like charge storage in a sense, in that if you want to change the voltage applied between to a metal semiconductor contact, you actually have to change the depletion width. Does that make sense? Okay. So let's see what notes I have. So let's draw metal and N-type silicon. Okay, so let's say there's some depletion width like this. And let's say you apply a VA that's negative. This depletion width increases with VA less than 0, right? If you apply a reverse bias. So you're increasing the width of the depletion region. Okay, so in reality, what's happening in this circuit is that when you apply this negative voltage, you are removing, okay, so this is N-type silicon. It has a lot of mobile electrons. You're actually removing electrons, the majority carriers, from the N-type silicon. So basically you're uncovering more ionized dopants, right, by moving electrons out of the silicon. And then electrons are going into the metal, to basically compensate for that. Okay, so in essence, in order to change the voltage, you need to actually add or subtract charge to both sides of this device. Does that make sense? Okay. So because of that, we call this effect a small signal capacitance. In other words, if you want to change, it's not a capacitor, of course, because it lets current flow easily in one direction. So the key is if you want to change the voltage across this metal semiconductor junction, you have to add or subtract charge from both sides of the junction, okay? Because you have to change the depletion width. So therefore, some displacement current has to flow, and that's going to depend on the change in voltage. Okay, so the notation that we use in electrical engineering is little v denotes a AC quantity, so a small change. Okay, so little v sub a is just a small change. Okay, so v sub a is just the total applied bias. So if you want to change the applied bias by a little bit over time, then that means you have to flow charge into or out of the semiconductor over time. And the amount of charge that you need to flow in and out is going to be proportional to the capacitance. Right? That's the definition of the small signal capacitance. Okay? So you can think of this as a parallel plate kind of capacitor device. I somehow erased that. So when you increased the width of the depletion region with an applied bias, VA minus is less than 0. Essentially, think of it as, okay, the depletion region is kind of like not a very good conductor, so think of it as like the dielectric portion of your capacitance, okay? And then you're basically adding more positive charge to the right side of this capacitor. That makes sense? So when you move electrons out, it's kind of the same as adding positive charge to the right side of this capacitor, right? You're uncovering positive charge when you remove electrons. So it's like adding positive charge incrementally to the right side of this dielectric, this depleted region. Okay, so effectively then, you're adding and subtracting charge at the edges, what is this going on? At the edges of the depletion region. Does that make sense? So the width of that depletion region, okay, so if you make small changes in the applied bias, you're essentially adding or subtracting charge at the edge of the depletion region. And so the separation between like negative charge in the metal and positive charge that you're adding in the semiconductor is equal to the width of the depletion region. Okay? Does that make sense? So the small signal capacitance is proportional to the area of this metal semiconductor junction, and it's proportional to the dielectric permittivity of that capacitor, which is the depletion region. So that's the permittivity of the silicon, and this inversely proportional to the width of the depletion region. So you're adding and subtracting charge, depletion width apart from each other, incrementally. So this is keep in mind this is small signal capacitance. It's not a real capacitor. Is this really a definition of? This is not a definition of W. This is the definition of small signal capacitance for a metal semiconductor junction. Right? So the key is that qualitatively the concept is that if you change the voltage, you need to change the charge stored in the junction, and that charge is added or subtracted at the edge of the depletion region, and so the charges that you're adding and subtracting are from each side are essentially separated by W, and the dielectric material is the semiconductor. Okay. All right. So this is just algebra here. Plug in the equation for the expression for W, and you can find then that 1 over the small signal capacitance is a linear function of applied bias. So if you plot, I don't know why this screen is, you plot 1 over c squared as a function of the applied bias, you'll find that it's a straight line, roughly, if it's a constant doping. So this slope will give you the dopant concentration. And notice that we usually make this measurement under reverse bias. Okay, so okay, so this slope, right? This slope is basically what you can measure. So experimentally, you can change, apply like a sinusoidal signal to this metal semiconductor junction at each reverse bias value. So you let's say apply -1 volt, change a little bit, like add like plus or minus 10 millivolts, see how much displacement current flows, and you can get the capacitance. And then you do this for each value of VA like this. So you can experimentally measure the small signal capacitance as a function of the applied bias. And from the slope, you can find the dopant concentration near the junction, and you can extrapolate this down to find the built-in potential. So this is one way that you can experimentally figure out the actual work function, the barrier, the Schottky barrier height for a real metal to semiconductor junction, right? Because if you know the slope, then you know the concentration of dopants, so then you know the work function of the silicon. And then if you know the work function of the silicon and you know the built-in potential, you can deduce the Schottky barrier height. Okay? And I mentioned to you, Schottky barrier height is usually never ideal, so you have to experimentally measure it. And so this is one way to do that. And the reason why we only take measurements in reverse bias is because to measure the small signal capacitance, you have to measure the displacement current. Under forward bias, there's too much diode current flowing, and you won't be able to detect the displacement current. The displacement current is small, so you can't your ammeter is only going to measure the total current. They don't care if it's displacement or DC. So basically, you want to make this capacitance measurement to measure the displacement current only when the DC current is small or negligible. So that's under reverse bias. Okay, so you make this capacitance measurement under reverse bias, so the primary current that flows is displacement current, not the diode current. That way you can get this kind of a plot and really figure out what your true Schottky barrier height is. So on the homework that's being assigned today, you'll qualitatively sort of look at this. Okay? And also for the homework, I'll make you go through this by yourselves, I guess, looking at metal to P-type semiconductor contact. Okay? But maybe I'll go over this quickly at the beginning of the next lecture. So just a reminder, the quiz will be given at the beginning of the next lecture. Please show up on time because you'll have only 25 minutes to conduct it. Okay? Thanks.